You see all those big flashy numbers when a new CPU comes out, right? Well, today, we're going to pull back the curtain and get into the real math that drives processor speed. We're going to calculate what's actually happening deep inside a modern CPU pipeline. So let's just dive right in.
Okay, so we all know pipelining is what makes modern CPUs so fast. But have you ever stopped to ask, by how much? Like really, how much faster? That's the core question we're tackling today. We're going to look at the perfect, on-paper scenario versus what actually happens when the code hits the silicon.
So just as a quick reminder, think of it this way. A processor without a pipeline is like one person building an entire car from start to finish before even touching the next one. Super slow. But a pipelined processor? That's the assembly line. You've got different stations, each working on a different car at the same time. The dream, the absolute goal here, is to finish one brand new instruction every single clock cycle.
All right, first things first. Let's start with the best-case scenario. This is the big promise of pipelining, and we're going to calculate what that ideal speedup looks like.
The key metric we're going to use is called speedup. And honestly, it's a beautifully simple idea. You just take the time it took the old, slow, non-pipeline processor and divide it by the time it takes our new, super fast pipelined one. That's it. So let's actually put this formula to work. Okay, time to get our hands dirty with a real problem. Let's say we have an old single-cycle processor. It takes 500 picoseconds to get through one instruction. Now, we swap it out for a shiny new 5-stage pipeline, and its clock cycle is way faster at 120 picoseconds. The big question is, what's the speedup? How much better did we actually do?
And the math here is pretty straightforward, which is nice. We just take that original time, 500 picoseconds, and we divide it by our new, zippy clock cycle of 120 picoseconds. And whatever pops out, well, that's our ideal speedup.
And boom, there it is, 4.17 times faster. Now wait a second, you might be thinking, hey, it's a 5-stage pipeline, shouldn't it be 5 times faster? And that's a great question. We'll get to why it's not a perfect 5x later. But still, over 4 times faster, that's huge. But remember, we're still living in a perfect, ideal world here.
And here's where the bubble bursts. That perfect, smooth-running assembly line, yeah, in the real world, it gets gummed up. All the time. So what happens to our nice, clean math when things inevitably go wrong? So let's meet the #1 villain of our story, the branch penalty. This is what happens when the CPU hits a fork in the road, like an if-then statement in your code. It has to guess which path to take, and when it guesses wrong, bam! The entire assembly line screeches to a halt. It has to throw out all the work it just did and start over. Let's see just how much that hurts performance.
Okay, so let's set up a more realistic scenario. We've still got our 5-stage pipeline, and in a perfect world, its CPI, that's cycles per instruction, is 1, meaning 1 instruction per cycle. But here's the catch. 20% of the instructions are these pesky conditional branches, and every single time one of those pops up, it causes a stall that costs us 2 extra clock cycles.
Right. So to figure out our actual real-world performance, we can't just pretend the CPI is 1 anymore. That's out the window. We have to calculate something new, called the effective CPI. This is the number that's going to tell us the truth, warts and all.
And here's the formula we're going to use to find it. Our average CPI is just the ideal CPI, which is 1, plus a penalty. And that penalty is just how often do the bad things happen, multiplied by how bad are they when they do. So it's the branch frequency times the branch penalty. Simple as that.
So let's plug in our numbers and see what we get. We start with our ideal CPI of 1.0. Then we have to add that penalty. So 20% of our instructions, that's 0.20, have a 2-cycle penalty. So we multiply those together. 0.20 times 2 is 0.4. Add that to our starting 1.0, and our new effective CPI is 1.4.
And let that sink in for a second. We went from a perfect CPI of 1 to a real-world CPI of 1.4. That means we're spending 40% more cycles to get the same amount of work done. That is a massive performance hit, all because of those branches. Suddenly that dream of 1 instruction per cycle feels pretty far away.
Okay, so this brings us to our last piece of math, and it's basically the final report card for our pipeline. It's called pipeline efficiency, and it tells us, flat out, how much of that theoretical performance we're actually getting.
This one's super easy to calculate. You just take the speedup you actually got and you divide it by the number of stages in your pipeline. I mean, think about it. If you have a 5-stage pipeline, you'd hope for a 5x speedup, right? If you got that, your efficiency would be a perfect 100%. But do we ever get that?
In fact, let's circle all the way back to our first example. Remember that one, the ideal one? We had 5 stages, but our speedup was only 4.17. So let's run the numbers and see what the efficiency was for that supposedly perfect scenario.
So, you take 4.17 divided by 5 stages, and you get 83.4%. Wow! So wait, even in our best case, everything is perfect calculation. We were still leaving more than 16% of the performance on the table. What's going on here?
Well, it turns out you can never really reach 100% efficiency, and there are a few big reasons why. First, you've got unbalanced stages. If one station on the assembly line is slower than all the others, the whole line has to slow down for it. That's a bottleneck. Second, there's pipeline overhead. Just the act of passing the work from one stage to the next adds a tiny bit of delay. And finally, you've got the fill time. At the very beginning, the pipeline is empty, and it takes a few cycles just to get it filled up and running at full speed.
Okay, so we've crunched all these numbers: speedup, CPI, efficiency. But why does any of this actually matter outside of a classroom?
It matters because this math is the language of CPU design. This is how engineers make decisions. Every single choice is a trade-off. Do you make the pipeline deeper to get a higher clock speed? Well, you can, but now your penalty for a branch mistake is way worse. These formulas, speedup, effective CPI, efficiency, they're not just numbers. They're the tools engineers use to navigate these incredibly high-stakes balancing acts.
And that really leaves us with a final fascinating question. We started with 5-stage pipelines. Today's processors can have 10, 20, sometimes even more stages. Every time they add a stage to chase that extra performance, the problems we just calculated, like branch penalties, get exponentially worse. So, as we keep pushing the limits, what's the next big bottleneck? What's the next problem that CPU engineers are going to have to calculate their way out of? Something to think about. Thanks for diving into the math with me.